very happy to introduce here today a very passionate software developer, scientific researcher, job entrepreneur, a developer of a bunch of cool libraries like Speech Portal, Synapse Grid, typed ontology. And today, while talking about typed ontology, we will talk about relational algebra implemented in terms of typed ontology. Arseniy Zhizhelev. Hello, Arseniy. How are you doing?
Hello, Grigory. Thank you for the introduction. And here we're going to present relational algebra in Scala3. So first of all,
before you start, let's really quick mention to everyone that all questions are very welcome during the talk, and send them right away into the chat. If there will be time, we'll interrupt Arseniy, and he'll be more than happy to answer all the questions. If not, then you can always join the Happiness Q&A room to answer all the follow-up questions. That's all. I'm sorry for interruption. Please
yeah, welcome. So questions are welcome. So first of all, this Scala3 is very great language, and I appreciate Martin Odesky's work that this great foundation for type level programming. So now we have this dependency object typed system with some mathematics behind it. So I believe in brilliant future for Scala. So today I'm going to talk about three things. First, in short, I'll touch the type level programming things, like a couple tricks, a couple of methods that I'm using in relational algebra. So I'm going to touch on that. Then I'm going to say a few words about typed ontology, how to represent data structures in such a way that you can, it's like schema modeling, so that you can work with schema separately and the data separately. It's not case classes. And then we'll go to relational algebra, how we can implement almost all relational algebra operations at type level, without any runtime part, and see how it looks in Scala3. All right. So it's like a reminder. Some of you have used type level programming. Some of you have read about it. So I'm going to talk about a few things here. So I'm using pattern matching node types, which were introduced in Scala3, and recursive types. Actually, recursive types were available previously, but now this works just very smoothly. And there is a super cool operation which is called Inline, which allows you basically, it's not type level programming, but it's compiled time programming. It's part of meta programming technique. So when you use Inline, you actually create a program that will be executed, not really executed in terms of Turing system, but actually it will be more like lambda calculus substituted, right? So your program will be actually executed by substituting. I'll mention const value tuple, arrays value, and value of. And there is some limitation, which will probably be released at some point. So we'll touch on that as well. So the first thing is that we can match on types in Scala3. And this looks really simple to what you would expect if you pattern match on values, right? Here you use type constructor, and you can receive or bind type argument with some new name, and then use that name on the right-hand side to construct new type. For example, here we just use list X and then provide X, but we could also construct a new type option of X on the right-hand side. So this is a very nice feature. You can do, using type level computation, you can do some interesting things. For example, you can actually calculate some numbers. This is a type level function where you pass 3 arguments which are types. So Scala3 now has great support for singleton types. So every number is also present on the type level. So for example, this 0 is both value number and it also type of 0 and is subtype of int. So this is really important thing. This n is actually a type, and the result of all this calculation is another type, right? So here, if we pass to this argument, to this type function, if we pass singletons, which will look just normal numbers, we will receive new type, which will also look like a normal number. And this s is actually +1. So you can consider this s as an increment or successor of x. This all has great support at compiler level, so it works like fast. It's not that slow church numbers that we have used previously. We can, so as you see, the previous one was on types, and now we're talking about similar function, but implemented using this inline capability. So we use normal function, normal values, and we use normal, like almost normal, right? So we could put here 0, or we could put here some other number. It's like normal value. And compiler will substitute this function at compile time. That's very important, so that every calculation will be done at compile time. A good example is power, and it is provided in tutorial. So you can implement some function, and then during runtime, this function won't even exist. Only its result will be inlined as a constant. And there is const value. Const value provides us a mechanism to go from type level computation back to values. So compiler can execute this function, type level function, at type level, construct singleton type, and then const value, if it's a const value, it will produce the actual value. So this f3 is actually a number 5, and it has type 5, which is the result of this function. And it also has type int, of course, and we can say that it equals to 5, finally. There is similar function for tuples, because tuples are like constructed from ordinary values. So that's why it requires this separate function, const value tuple. I'm not sure why is that. Probably eventually that would be just const value, but now it's like that. So this is at type level. So you see this brackets, right? This number 1 is type 1. This hello is type of strings hello. And then we create a value, and the result of this function exists at the value level. So we can compare it with normal tuple of 1 and hello. The one thing that is not available in Scala at the moment, probably it will be at some point available, is this one. So if we have some trait, some abstract class or things like that, with type element in it, some type, we cannot, so this will not work. It will produce you this error. So this type projection for some argument, like, right? So this looks like a normal function that receives a collection, C, some type that derives from collection, and then we want to get element out of it. And this doesn't work. So this is an error that we see. What is suggested is to use dependent types. So this works. So we define some normal function which receives some value of type C, and from that value we can select type. So this works. This doesn't. So that provides some, this puts some limit constraints on how we can implement relational algebra. So if there are any questions, you have the opportunity to ask. probably this is all known things. So now I'm talking about less known thing. So it's about typed ontology. So we all know that the recommended way to deal with data is to create case class, right? So you create case class, you define some fields and types. While this is very easy to do and it's straightforward, it's not flexible. So you cannot represent missing values. So you define, for example, here we define a product ID, name, price, and if you do it in case class, you won't be able to represent that ID is not yet exist. It does not yet exist. So when you want to insert some product into a database, you only have name and price, and ID you don't have it. And what are your options? You can create a separate case class like product data, or you can create ID optional and then use that somehow substituted on the fly. So this is not very convenient. The reason for this is because in different parts of our program, we know some partial information about some entity. For example, this product, the price may be different at different places. And it may be like we may have it at some point, or we may not have it at some other point inside the program. So, for example, if you read some data from JSON, you may have some errors parsing the price. You should be able to work with whatever data you have, but some of the data is not correctly parsed, so it's not represented correctly. So you need a mechanism to work with partial data. Or user enters a large form with hundreds of fields, and then in this form, the user wasn't able to fill all of them correctly, right? You need to represent this partially correct state somehow. So typed ontology provides us the way. So we define columns. ID, name, price is just column, which provides, it does not contain the data. It only describes the schema. Every column has type of the value that it contains, like A here. After we defined the parts of the schema, we can now construct a new schema out of whatever we have. So we just create a tuple. It's this is a normal tuple is star, right? We use hash colon, because we in parallel we construct schema, like put some additional information here. But never mind, this is very similar to tuples. So we can construct whatever schema we want, and at type level this will be like that, and at value level this will be like this. And this is schema that represents some potential instance of this product. So in this case, we have all the three fields, right? In other case, we can have just name and price. And it's easy to construct this kind of schema. You just represent it here. This is like just a definition of this hash colon, how we construct. It's very similar to tuples. We just have a constraint so that we can only use properties or attributes or columns to be added here into the schema. In parallel, we construct tuple. So tuple in standard Scala library, it has type function map. It takes one tuple and then applies another type function to it. This is very cool if you just think about this, that we are applying some map at type level. So the end result here is the tuple of types. So if we have this product int string begin, so these values will be a tuple of 3, int, string, and begin. So this is the result of type level programming. So we didn't construct these values manually. We obtained it from properties using this mechanism. And we can actually check that it works, right? So we can create a tuple and it will fit here and it will be equal to this one. All right. Alternative representation of the same product is typed map. So we can use property to get value. So you can see here that we define type class for some representation of data, right? And if we have that representation of data and we ask for a property, we can return the value if it is present. For example, we can use sorted map or just hash map to contain the values. And if this property value exists in this map, we will return some. If it does not exist, we'll return none. And as well, we can perform the update operation. We can also have tuple of options. So similarly, we take tuple of types of each field, right? ID, string, big int. And we apply some higher level function on it. So it's type constructor. So here we use it to apply option for it to each type. So as a result, this will be a tuple of option int, option string, option big int. So this now we have the type to represent partial data. And we have either values, right? So we can, so either, for example, we have some error representation. It's either string or an exception or some parse result error or things like that, right? So we represent this as E. And now we apply using type lambda. So this is also the feature of Scala3, type lambda, which says, okay, for any type of column, construct the type of column that could be incorrectly read from somewhere, right? So it's either an error or the value of it. And this is type level lambda. All right. So now we are ready to having all these instruments like types ontology plus Scala ability to work in type level and using inlines, we can implement the following operations. We define some relation. We then can implement projection of from one relation to some other relation, cross product of two relations, including joins, select some elements there, and work like precisely with the schema. So we can replace some column, we can calculate column. So this is like basic operations, like most of the operations that are required for relational algebra. All the which are not implemented could also be implemented in a similar way. Probably this is just the matter of doing the work. So relational algebra is based on relation. Relation has a schema that contains some columns, as we have previously seen, and data, the rows for identically typed rows. So we can use list for representing the data, or we can use vector, or we can use stream, or we can use whatever. For example, we can use some data set or things like that, data frame, RDD, or whatever, something that contains data. We just, because we have schema, we know the type of data. So we use this V to represent that something that contains elements of this type. What is projection? So if we have one schema and we have another schema that contains subset of properties, right? We can just remove unneeded data and probably rearrange this available data, and we obtain new tuple. This is important because if you have large table with hundreds of columns and you only want like 3 columns, you need to be able to project whatever data you have and receive only whatever you need. And the slight nuance here is that we are doing it from the perspective of schema S2. So and at schema S2, we have direct access to our properties. And now we just select each of our properties from schema S1. So this is the implementation of projection. The type of the result, when you do the projection, the type of the result is immediately available. You know it because you have constructed schema S2 and it's already available. So nothing happens at the level of type. However, you need to create a function that will convert data from schema S1 to schema S2. So here is how it goes. So we define this function and note that it's inline function. Inline function, right? So this function will be executed and will produce some function at compile time. So here we can see what is happening at compile time and what will happen at runtime. At runtime, there will be a simple function that converts one tuple to another tuple. At compile time, we know about schema, we know how to convert, and all these things happen at compile time. And this is how we construct it. So we just construct property getter. Property getter is a function that extracts the value from a tuple. It's like just accessor from the tuple. Then we use recursion to construct for the rest of the properties. And now here we are. So this is our function that we constructed. It takes the original tuple and then using this getter appends the value of the property to the rest of the schema, to the rest of values. So basically it's pretty straightforward implementation. Yeah, we combine a single tuple. Cross product. When we want to do a cross product, we have two relations and we just want to pairwise concatenate all of them, right? So we first, the resulting relation will contain all the columns from first relation and all the columns from the second relation just concatenated. So the first thing we do is concatenating the schemas. And this is done using recursion. So here it is so we append our property to schema being appended to another schema. So if it's empty, then it will return just schema S2. And if it's not empty, we just append our property and use recursion to do. All these recursive operations happen at compile time because all of these are inline. Yes, and so there are two options in Scala3 how to implement this thing. We can use pattern matching, as we mentioned previously. And here we are using abstract types. So this type is defined at select trait. And then the implementation is in each of the cases. So empty schema and non-empty schema also implement this thing. And then we construct a function. So having this conversion, we construct a function that will do the concatenation. You see that we have to pass the result of appending schema 1 and schema 2. This is just because of the limitation that I mentioned previously. So the absence of this, generic projection. Instead, we use dot types, and we can still work, but we have to pass the schema 3 ourselves. However, on the alternative, we could construct it on the fly, because having our schema current and schema 2, we can construct it on the fly. However, this is seemingly not possible. Probably possible, but not. I don't know how to do that. So we are passing schema 3 here. It's not that big problem. And we just concatenate values and cast. So I'm not sure why we have to cast here, because basically the types match. So the type of this tuple concatenation is exactly what is declared here. The difference is how we construct this type. So schema3 constructed in like appending things, and this constructed in a slightly different way. So probably compiler cannot prove that it's the same type. However, using this cast, it works. So in a couple of places, we had to use cast to make sure that we match the type that we constructed ourselves, because the operation may be slightly organized in a slightly different way than the type operation. Now, the only thing that we have to do is actually apply the thing to data, right? So we have constructed a function that will concatenate values, and now we just run through all the rows of the one relation, all rows of the other relation, and we just concatenate them. We construct this new relation with new concatenated schema and the values that are produced by this like cross product of the values on the left and right. The important thing here is that this creates a new tuple. It's not a tuple of two tuples. No, it's concatenation of two tuples. So it's a single plain tuple, the resulting thing. All right, we seems to be a bit out of time, so I'm going to slightly increase the speed. So in a similar way, we perform join on a foreign key. We can work on replacing and renaming columns, right? So having the schema, we can replace one column with another column. And if it's the same time, we call it rename. So basically, this is like this, right? So we have two properties, and they are of the same type. And we can replace one with another. We can calculate column. How we do this? We provide a new column, and we provide a function that is from row to this property type. So this is possible to construct, to prepare new column, and we just apply it to each row, and here we are. So this is a new relation with the new column. We can also implement some expression DSL as usual, right? So instead of writing functions that work directly with row, we can express our intention. We create DSL that mention just column names and some operations on top of those column names, and then this DSL will be translated to actual functions that work with row. And because this translation happens at compile time, the resulting will be just normal functions that work with tuples. So here is an example of how we deal with properties. This is a DSL operator, some constant, and the same can be used for filtering things. So we can compare, like if we want to filter some orders by order ID. All right, so this is basically our implementation. And now I would like to say a few words about where it could be applied. So if we have Slick and we apply this type level computation relational algebra, this greatly simplifies working with Slick, I guess. Because I worked with Slick previously, it's a great library. There were some like limitations on the way how you work with relations. If we work with Spark or Flink, then it will be helpful because we will be in a better position, right? So we can select our columns in a type safe way, and we can construct our operations also in a type safe way. And the resulting constructed operation can be transferred then on through the cluster. If we design our application ontology driven, right? So we define the ontology of our application, and then every single part of our application relies on that ontology to infer its logic. So we define the schema, and then we can infer from there. We can infer JSON codecs, XML codecs. We can infer a database schema. We can infer user interface parts, with interconnections. Like if there are foreign keys, we can connect directly in the user interface. You can click and see directly go to the object that is represented by that identifier. We can write generic programs that work with data about entities. So there will be events about entities, or like we can have versions of entities, and these are derived things. So we can write a library that work with arbitrary ontology and provides these higher level data services like events or history. So the library is designed in the following way. So there is some couple things here. The data runs at some application level. The application actually will work with data represented in instances, either tuples or JSON or typed maps or things like that, probably case classes. Ontology contains this schema that about how our data is structured, like product, order ID, the column IDs, foreign keys, how this is connected, and things like that. Then we have some meta that allows us to create ontology, to describe our schema. And we have simple meta library, which is like an example of meta library. All property have just name, and we use it to identify properties and to read from JSON and so on. All right. So I didn't do like actually performance tests. Probably I'll do it eventually. So like theoretically, this all happens at compile time, and at the end we only have tuple operations. So it is as fast as tuple are working in Scala. So that's why this provides us potential optimization mechanism, right? So we can, if we experience any kind of, if tuples is not enough for us, right? So you know we do not require storing complex data structures at runtime. It's just tuples. But if we have, if tuples is not enough, we can use case classes because in case classes we benefit from specialization of fields. So if there is a lot of numbers, integers, longs, it will be more helpful. All right. Oops. So what we presented here is a relational algebra that works at type level at compile time, and what the resulting program works only with tuples. This provides like a lot of benefits, right? So first of all, like if we create a library like Slick, we will be able to perform all those operations in a type-safe way, like in a slightly better way than it's currently implemented. Because currently Slick has some rough edges on how to deal with schema. Now, having this Scala3, it will be much, much better. All right. One of the things that I'm going to do is to support this nested schemas. So when you have some field of another type that could, in its turn, could be described by schema. So this is the next thing to do. All right. So now we are done.